Hello and welcome to this virtual presentation, and thanks for stopping by. Let me introduce myself first. So my name is Paolo. I'm a third-year PhD student at the University of Notre Dame in Indiana, and I generally work with physically based numerical models to simulate atmospheric processes, all right? So in this 15 minutes, we're going to talk about wind energy, mostly, some of the challenges that we face in estimating wind resources, as well as avoiding important financial losses related to wind projects. And then in the end, I'm going to talk about some of the progress that we are making to contribute to solve some of these challenges, all right? So let me start perhaps from some well-known facts before I actually delve deep into the main topic of today. So in 2014, wind energy covered only 2% of the total energy demand, and the total energy production from renewable resources accounted for around 18% of the total energy demand, all right? So now the renewable energy roadmap from the International Renewable Energy Agency suggests a 2030 scenario, so all the way up here, with a much bigger role from wind energy, first of all, so 11% should be covered by wind energy, and also twice as much renewable energy sources in total, so 36%. So this would be the pathway basically to cap the CO2 emissions below the widely accepted climate change tipping point of 2 degrees Celsius, right, in increase in temperature with respect to the pre-industrial levels. So where do we stand now? Right? What's the current status? So this is the global energy status with around 74% of energy still produced by non-renewable electricity and only 26% by renewable sources. So we are somewhat in good track, right, to the 2030 roadmap goal. Now, wind energy produced 5.5% of global electricity in 2020. So again, still good progress. I mean, since 2014, where only 2% was produced, but there is still a long way to get to the 11% suggested by the renewable energy roadmap. Now, if we look at the costs of wind energy, and here is the latest LASO report, well, wind energy seems to be cost competitive with other conventional generation technology and typically cheaper than some of their counterparts, right? So what is actually limiting a rapid expansion of the wind industry, right? Of course, there are multiple problems, right? Like noise or impact on wildlife or intermittency, right? But sometimes we just have some challenges in accurately characterizing the wind resources in the planning stage for new wind farms. And here is one example of that, all right? So the map on the left, which comes from a paper in 2018 by Lunacek and some collaborators, shows that the correlation between the expected generation of a wind farm before its construction and the actual power generation, so after it's actually built, can be very, very low. Like in some cases, I'm looking at the Northwest here, for instance, in the US, it can be as low as 0.2. Meaning basically that the estimation of wind resources were very different from what happened in reality, right? So if we look at the type of error that we're making, well, we tend to overestimate the wind energy output, and you can see this from these plots here on the right. This is basically the distribution of error, right? And most of the mass in this distribution is concentrated in the negative values, which means overestimation of wind energy resources. So basically on the planning stage, we're saying, well, we're going to have a lot of wind resources. And then when actually the wind farm produces is much less than what we expect. And this causes some sort of financial problems for wind farm operations that, of course, we want to avoid, right? So what are some of the challenges in wind resources assessments? Well, typically, especially in regional scale applications, we rely on models or reanalysis products that are somewhat coarse, right, in resolution. And this is because reanalysis products are typically global and they cannot really resolve like local characteristics of the flow, stuff that is, I don't know, dictated by complex topography there, right? And here is one example of that, right? On the left, I plotted a wind speed at 10 meters from one of our numerical simulations in Saudi Arabia with a resolution of 12 kilometers. So what a typical reanalysis product would look like, right? Now on the right, you see the same domain solved on a 440 meters grid, right? And you can see that there are large differences between these two maps. So if I were to identify basically the optimal locations for building a wind farm here, I would get two different answers depending on the adopted resolution, right? And this, of course, is something that we want to avoid. So the question becomes, well, why don't we just crank up the resolution of those models as much as we can? So it turns out it's not that straightforward, as we face some challenges when we move to unexplored ranges of resolution around 1 kilometer, which we usually refer to as the gray zone of turbulence. And let me explain in basically a minute what is this gray zone of turbulence. All right. So you can imagine that modeling turbulence for atmospheric models is definitely key, as turbulent motions mix all sorts of things in the atmosphere, right? From heat to momentum, moisture, pollutants, and whatever else. So traditionally, we have two well-established ways of modeling turbulence. One applies to very low resolution models, for instance, global climate model or mesoscale model, that typically solve these Reynolds average Navier-Stokes equations, all right? The other end is instead this LES modeling or large eddy simulations modeling, and it's substantially different, basically the way that we model turbulence, all right? So here on the left, the assumption behind each of these global models or mesoscale model is that no turbulence is explicitly resolved, right? So the largest turbulent motions occur with length scales on the order of 1 kilometer, because we don't really have enough resolutions to resolve these turbulent motions, right? And so we had to add some parameterizations to account for whatever is unresolved. So all the turbulent motions that are unresolved in the model, right? On the other end, so here on the right, we have LES modeling, right? In which we assume that large turbulent eddies are indeed resolved, because now we have the resolution to do so, right? LES modeling, they can have resolution, I don't know, around 100 meters. So if the turbulent motions have scales of 1 kilometer, well, the largest scales of turbulent motions are actually resolved by the model itself, because we have the resolution to do so. And then the rest, of course, we still need to model. So the problem is that we don't really know what to do when turbulent motions are only poorly resolved. So somewhat in between these two different world or two different well-established turbulence models, right? And this is basically what we call the gray zone of turbulence. This is particularly interesting or important to figure out when we try to crank up basically the resolution of mesoscale models, right? But also when we want to force microscale LES models as well, right? Because usually we force this LES model with realistic mesoscale boundary conditions. And if we're forcing this thing, I don't know, at 100 meters resolution, then probably we're forcing it from a 300 meter resolution, and that falls into the gray zone area. So we want accurate boundary conditions for basically our LES models as well, or like, I don't know, wind turbines model and all these sorts of things, right? So it's very important to deal with this problem, but we don't really have an answer right now. And that's where our research is sitting, basically. So the research questions are the following. The first one is, what is the magnitude of the errors introduced at gray zone resolutions, at least relative to other factors that influence real simulations? And the second one is, well, can we find some modeling strategies that can be effective in mitigating this problem? So to answer this question, we set up a new set of numerical experiments. And these are basically centered in Saudi Arabia. And the reason why is because we have a project related to wind energy in Saudi Arabia, but also it's because in Saudi Arabia, there are very strongly convective conditions. And we know that this kind of gray zone problem occurs mostly in very strong convective conditions. So it's a very, very interesting domain to study. All right, so we have 6 nested domains. The outermost is 12 kilometer resolution and the innermost is 50 meters. So we have both ends of the spectrums, if you want to see in that way. And we pass basically through the gray zone, all right? And the simulation set comprises basically 9 runs that aim to assess different strategies to model turbulence at gray zone resolutions, right? So we did a lot of analysis basically on this experiment. So we ran this experiment, solved these equations on supercomputers, and then we ran a lot of analysis to understand more about the gray zone and to answer those 2 questions that I was mentioning before. So Q1 was the following. What is the magnitude of the errors introduced at gray zone resolutions relative to other factors that influence real simulations, right? So I guess this figure summarizes the main findings for Q1 pretty well. So let's focus on the surface layer, the mixed layer for wind speed, which is eventually what matters, right, for wind energy purposes. So the bars that you see here, they represent the RMSE, which basically is an aggregate error metric. And the lower the RMSE, the lower the error, right? So as you can see, the lowest error is obtained for the microscale simulation here, but the gray zone errors are somewhat comparable. So all these are gray zone errors, and they are somewhat comparable to the mesoscale one, right? And the gray zone error, eventually, it depends on the modeling strategy that we apply there, right? And I'm going to talk about this in a second, but basically we had 8 different simulations at gray zone, and we changed some things to test different options to overcome these issues. So let's talk a bit about these potential strategies that we can use at gray zone resolutions. Again, this is still very high level. I don't want to go into all the technical details that go behind this, but just to sort of give you an idea of what can be done. And then, of course, if you have any questions or other things, you can read some of our work, or you can just email me, and always very glad to answer any kind of questions. All right. So the first way that we can solve this issue is basically to suppress resolved turbulent structures from the grid, right? If the problem is, well, we only have these poorly resolved structures that can cause some sorts of issues, why don't we just suppress them, like completely suppress them, right? And we can do this basically by increasing the horizontal diffusivity in the model, so some coefficient, tweaking some coefficients in the model. And we can manage basically to kill some of the convection or the turbulent structures that are happening there, but it's probably not one of the best ways of solving these issues. Perhaps, I mean, here I'm showing the same thing. Here you see the fluctuations are basically dampened compared to the regional simulation here, in which you have much stronger turbulent structures. Perhaps a more efficient way of doing this is to introduce scale awareness in the parameterization. So it's basically the opposite of what I was trying to do before. So instead of killing the turbulent structures on the grid, we just retain these turbulent structures, but we introduce some sort of scale awareness in the parameterizations. Basically, I'm saying, well, in the parameterizations, now I can lower the amount of subgrid mixing done by these parameterizations, right, with some sort of functions that depend on the resolution of the model. And then, I mean, the rest of the mixing, it's not going to be subgrid, but it's going to be resolved by these poorly resolved structures. And that's kind of the idea behind this second way, and it seems to be more promising. Again, if you look at the errors here, the scale aware, when you see scale aware, I mean, here I'm testing a lot of different things, but when you see scale aware, usually it entails lower errors in the surface layer and the mixed layer, which are the layers that basically are more, we are more concerned with when we talk about wind energy. So this is kind of an overview of what can we do. For future steps, we are thinking to address also Q3, so all the wind energy implications that come from this, right? How these errors basically translate into wind implications or wind energy implications. Do they matter a lot? Do they not matter? This kind of question we're trying to answer. And the other thing is to add turbines to our simulations and see the implications from the wake effect. So here we have some preliminary results that we still need to analyze more, but basically wake effect is another reason why we are sometimes overestimating the wind resources in wind farm projects, right? Because if we underestimate the problem that, like turbines in the back rows here, they receive much less wind than the one in the front rows, then again, we can end up underestimating these things. So thank you very much for listening. And of course, if you have any questions, you can email me at the email here, or probably we can find a way of interacting at the conference. Yeah.